So, last class we were looking at 3 position motion generation, and essentially if your first choice of moving pivots does not give you suitable fixed pivots, then you have infinity square choices for say the, so for example in this example of a dump truck, suppose the choice of x and y as your moving pivots gives you fixed pivots that say fall below the ground, or fall somewhere below the truck so that it may obstruct if it is going over a bump or something like that. It would be difficult to do that, in which case you may have to find other moving pivots on the bin, or you could possibly extend the bin if necessary to find suitable moving pivots. So, you would have infinity square choices, the x and y coordinates for x, and similarly an infinity square of choices for y. So, together you actually do have, even for 3 position generation, the choice of the moving pivots gives you infinity to the power 4 choices for your pivots. How many of those are practical is a different matter. Okay. The fact is you do have those choices. So, anywhere in the plane is what we say we can take these moving pivots to be. It is more likely, so for instance, that you may have constraints on where you locate the fixed pivots. Okay. It is more likely in real life that you will have constraints. So, if this is, you may say that this is the area in which I could possibly locate the fixed pivots. Okay. So, I may choose fixed pivots in those places, in that area, and now my task becomes, so for the same, so I have C1 D1, C2 D2 and C3 D3, and say I am given the locations of the fixed pivots. Notice they are OA and OB. It is very likely if I connect OA to C1 and OB to D1, it is not going to, C1, C2, C3 will not lie on a circle with center at OA. Similarly, D1, D2, D3 will not lie at a center at OB. The chances of that are pretty slim. So, basically you want to do the reverse of the problem. You are given the fixed pivots, you want to find where on the moving body you locate the corresponding circle points, so that for the 3 positions shown, those 3 points should move along a circle centered about OA or OB respectively. Okay. So, that is what we are trying to do here, and for that we will now use the principle of inversion. So, inversion tells me that the relative movements among the links does not change. Okay. So, I can change my frame of reference without affecting the relative locations of the links. So, in this case I am going to say, okay, instead of my being on OA OB, my fixed frame of reference, instead let me sit on CD at the first position. Okay. So, the coupler is not moving, okay. I am sitting there, that is my reference point, and I am going to look at how the frame or this OA OB, how that is going to move relative to me if I had the same relative motion. Okay. So, by inversion I am sitting on say the first position of C1 D1, and I am going to look at how OA OB will move with respect to me if I did not move, but OA OB moved instead. So, that the relative motion remains the same, the relative locations remain the same. So, if I look at the location of OA OB with respect to the second position. Okay. So, OA with respect to the first position, okay, this was C1 D1, this is OA OB. With respect to this, instead of my moving from C1 D1 to C2 D2, how do I move OA OB so that it maintains the same relationship in the second position? Okay. So, with respect to C2 D2, I can find the location of OA and OB like this. I basically measure the distances from, so I can locate OA like this with this triangle, I can locate OB with this triangle. Now, I transfer that because I am not moving, I am on C1 D1, I transfer that onto that first position. So, these triangles will be congruent to this C2 OA D2. So, C1 D1 OA dash is congruent to C2 D2 OA, and similarly C1 D1 OB dash is congruent to C2 D2 OB. Okay. So, I construct that, which means now even though I have not moved, if OA OB moves to OA dash OB dash, I maintain the same relative position. That is the same as OA OB remaining fixed and C1 D1 moving to C2 D2. Okay. Similarly, for the third position, I find out where OA OB are located with respect to C3 D3, and again transfer that relative location to the first position. So, OA dash OB dash, now I have OA double dash and OB double dash. So, OA double dash OB double dash will be from triangle C1 D1 OA double dash is congruent to, this should be C3 D3 OA, and C1 D1 OB double dash be congruent to C3 D3 OB. Okay. So, what I have done is, by inversion I know that if I sat on C1 D1 and did not move, OA OB should move first to OA dash OB dash and then move to OA double dash OB double dash for me to have the same relative motion. Now, look at this, if I have a 4 bar, let me do this. If I have a 4 bar chain, if I fix this with respect to this, this is going to move, these two pivots are going to move in circular arcs about these points. Okay. Instead, if I fix this, okay, this is going to move with respect to those pivots in circular arcs. So, essentially, okay, I sat on this as the fixed link, okay, and this moved from this to this to this. Okay. I want to find out where is the location on my fixed link, about the points about which these three, so OA, OA dash, O double dash A. What is the point about which those three will move along a circle? What do I have to do? Basically construct the perpendicular bisectors. I think I have them. So these are the three positions. So this becomes what? This becomes my moving, it becomes my 3 position problem with respect to CD. It is essentially the 3 position motion generation problem with respect to CD, C1 D1. So the point A1, if it was located on this body, okay, would be the point about which OA moves about a circle. Okay. Similarly, B1. So, if my body was shaped like this, okay, that right now that is my fixed link. Okay, this is where I would have to locate A and B, so that OA dash moves along a circular path from OA to OA dash to OA double dash, right. And similarly, if I pivot it, so if I connect, this would be my linkage. If I do this, then this would be my fixed link. So, I would connect, so again this becomes my fixed pivot actually. So, my link will not be the C1 D1, okay, it would not be, those would not be the pivots, right. These would be the pivots on the fixed link, and if I connect A1 to OA and B1 to OB, okay, then it moves, OA moves to OA dash to OA double dash, similarly OB moves to OB dash and then OB double dash. Okay. So, this, these are not pivots anymore, this would be my, but this is actually the inversion of what I want. Okay. OA, OB are my actual fixed pivots. So, this is actually the opposite of what you want. Okay. So, my actual linkage, it is the inversion of, I have OA and OB as my fixed pivots. Okay. So, my actual linkage is this, I pivot it at A and B, okay, and my coupler is shaped like this, or whatever shape that includes this. So, basically I have found what are the points for which OA and OB are the center points. I found the corresponding circle points on the moving coupler. I found the moving pivots. Okay. Hopefully, these will be in a location that is suitable for my application. Okay. But like in the case of the bin, it is very likely that the move, I can, if I locate fixed pivots here, I may find something somewhere on the bin that would be suitable for my moving pivots, because I have a larger area to work with, or even if I have to extend it, you know, if there is no other obstruction, then I have more flexibility to come up with a mechanism. So, in many cases, because you may also have a motor, that is, you know, you may have a driver diode connected. So, the fixed pivots will be the ones that are more constraining in the design. So, in those cases what you would basically have to do is use inversion to find your corresponding moving pivots. We will use inversion over and over also for function generation. So, you have to be very clear, it is very clear about the concept. Now, the third class of mechanisms would be your path generation mechanisms. So, usually when we look at path generation, we are looking at a point on the coupler moving through certain points. So, now you are not worried about the orientation of the coupler, okay. You only care about certain points on the coupler hitting certain points in your workspace, okay. You want, say you want a coupler point to come to C1, C2 and C3. If that is your design requirement, then it is actually easier than in the case of motion generation. It is less restrictive because you do not have the coupler orientation to worry about. So, C may or may not be a pivot. First of all, can C be a pivot? Can C be a moving pivot? If you say yes, you have to tell me under what conditions can C be a moving pivot. If C is a moving pivot, what do I have to do? So, I have to find the corresponding fixed pivot that is at, so that C1, C2, C3 lie on a circle. I could have more than, if I have more than 3 points, then that becomes a problem, but I could still have, we will see later that you can synthesize for more than 3 points for path generation with graphically. With motion generation, the 3 points, because on both the moving pivots you have that constraint, you could no longer find a circle that passes through those 3. 3 points is the limit to find a circle to pass through those. So, you could have C as one of the moving pivots, in which case you would do your typical and then you choose A as another moving pivot and you can synthesize the linkage. Okay. So, path generation is fairly simple, and again limiting positions, driver diode, the same things apply to all of these. Let us go to the case of path generation with specified fixed pivots. Say A0 and B0 are my fixed pivots, okay. And I am telling you that I want C1 to move to C2 to C3. So, choosing C as a moving pivot is no longer an option, okay. Then what do I do? So, I can pick some point A, say I am given in A0 A1, okay. I am given this. Now, I want to find out how do I design this for specified fixed pivots, so that it generates this path. C1 moves to C2, moves to C3, where C is a point on the coupler. Okay. From this definition of the problem, okay, I am given one moving pivot. What do I know that I could use to design this linkage? What are the conditions on A and C? I am giving you a hint. What did you say?
We can consider AC to be a rigid.
AC, because it is on the same rigid body. So, your distance AC is constant, good. A naught A1 is constant. So, what does that tell you? How will I know the orientation? So, that means you are saying A1 follows a circular path. Yeah, yeah. So, A1 follows a circular path. Okay. So, A1 follows a circular path and your distance AC is constant. So, A1 C1 will be equal to A2 C2 equal to AC, A3 C3. So, now I can find the location of A2 and A3 on this path. Okay. So, so A1 is a moving pivot. So, now what is this problem reduced to? It reduces to the 3 position motion generation. 3 position motion generation. Now, you have to move A1 C1 to A2 C2 to A3 C3 and you are given the fixed pivots. So, what would I do? Inversion. Do I have to sit on the first position or could I sit on any of the other positions? I could sit on any of those positions. If I sit on A2 C2, then I transfer the relative locations of A1 C1 with OA or A naught AB. I do not know why I used a different, I should just go with the same OA OB. And then for the third position and then put that with respect to the second position. If that is the position, that is not moving. Okay. So, I could sit on that, invert the mechanism, find the relative locations of OA OB with respect to those positions. Sorry. In this case, yes, absolutely, good. Yeah, in this case you already have one moving pivot. So, you only have to do for OB. Okay. So, find the relative location of OB with respect to the other 2 positions. So, here I have done it. So, this is, let me just go with, since I have used B naught. This is B naught as observed from the second position transferred to the first position. This is B naught as observed from the third position transferred to the second position. So, now these 3 points should lie on a, so the usual, draw the perpendicular bisectors, find the center of that and that gives me B1. So, my linkage is pivoted at A1 and B1. Okay, and this is my coupler. A1, B1, C1 is my coupler. And if I have this linkage, then it will move through C2 and C3 as well. So, the path generation problem essentially reduces to the motion generation. Yes. The distances of B, yes, 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 because A and B are on A and C are on a rigid body. So, I can find the relative locations. His question is, we can transfer the distances or the relative location of B with respect to A. You can do that. Okay. So, the relative location can be from there, you will still get the same moving pivot B. Okay. So, this is path generation. We are going to spend later, so this is just what we call path generation with precision points. So, precision points are the points that you want to hit in your design, you want to hit those points. Okay. So, we are not really looking at a path per se, we are saying we want a coupler point to reach certain positions on the plane, and I do not care about what the orientation of the coupler is when it is doing that. That is why it is a path generation and not a motion generation problem. Later on we will look at coupler curves. We will look at coupler curves in more detail, and coupler curves are most path generation problems come under this category of coupler curves. So, if it is not specific points, but a path that you want to trace using a 4 bar, then we actually look at synthesis of the 4 bar for certain types of coupler curves. Okay. And the coupler can have very interesting motions. Okay. You can have points on the coupler tracing very fancy curves. Points on the input and output links, not input, the crank or the follower are pretty boring, all of them trace circular paths. But the coupler can have very interesting, the curves generated by the coupler can have very interesting characteristics, and we will actually spend quite a bit of time on that later. So, I will not go into path generation using coupler curves right now, okay, because we'll finish these precision point synthesis as it is called, where you have certain number of positions and you want to basically hit those with the mechanism. So, this is path generation with the precision points, and we will look at coupler curves later. For function generation, there are two ways of looking at. So, function generation is you are coordinating, typically you are coordinating an input angular motion with an output angular motion. We have seen a special case of this already, which is your dead center synthesis. When you have a crank rocker and you are designing it for a specified time ratio, you are saying, okay, the crank moves through this angle when the rocker moves from one extreme to the other. Then when the crank moves through returns through the other angle, you have the rocker moving back. So, you have a rocker that is moving back and forth through a certain angle, and you are coordinating that motion with respect to the input motion, which is a full 360-degree rotation of the crank. So, that is a special case of function generation, but in many cases you may just want, have you all seen these recliner chairs? In that you will have a handle at the side. you move that through a certain angle, it reclines. Okay. So, you have, so or you may have a valve opening, okay. You may have a handle at a particular location connected to a somewhat farther away location where you are opening something. So, you move a handle through a certain angle and that opens something at a different location. You can also use other things, obviously you can use gears, you can use other types of machine elements to accomplish these sort of things, but here we are assuming that a linkage is your most suitable because they may be separated and it may this may be the most cost effective way of doing it. So, that is function generation. The name came about because earlier they would actually use it. So, they would actually design a function generator. So, this would be like, say you give some input x and you may get y equal to some function of x as the output. So, the input would be proportional to this x and the output would be proportional to y, and they could use that for even before you had computers and things like that, they would actually compute certain log functions or some complicated mathematical functions would be designed using linkages as an approximation. So, you could, and it would have a dial. So, if you give it a certain input, you can read out what the function value is using, that is why these are called function generators. The angles were coordinated in such a way that they would satisfy a certain function. Okay. So, the two methods that we will look at are, one is using inversion, basically again using the fact that the relative motion of all the links remain the same regardless of which link is fixed, right. So, and then we will also look at a method using relative poles, where we will look at that later, but essentially you will combine two of the follower rotations into a single equivalent rotation. So, we will revisit the pole that we looked at initially, and we will also define something called a relative pole. So, these are two methods that we will use for function generation. So, function generation is essentially, if you give the crank a certain angle, if you move the crank through a certain angle phi 1 2, 1 2 is 1 to 2, position 1 to 2, I want the follower to move through an angle psi 1 2. So, that is my design requirement. I move the input link through a certain angle and I want the output link to move through some other angle. If I want them to move through the same angles, what would I do? I would just have a parallelogram mechanism, right. I would just duplicate the motion using a parallelogram mechanism. Okay. So, again we will use the principle of inversion by saying, okay, instead of OA OB being my fixed link, I will sit on maybe the input link, and then my relative motion would be, the frame would have moved by an angle phi 1 2 with respect to me, okay. And then this angle, okay, would be, let us just call this alpha, this would be alpha plus psi 1 2, or if I reconstruct, okay, so this would be psi 1 2. Okay. So, I take this rotate, okay, first I rotate this whole thing like that. So, I could actually have this, and this would be psi 1 2. So, this would be alpha, this would be, this angle would be psi 1 2 minus a, no, plus psi 1 2. This is alpha, this is psi 1 2. Okay. So, this would be where B 2 would be if I observed it from OA A 1. So, I call this B 2 dash. So, what does this tell me about? So, I am sitting on this is my fixed link now. I am just looking at this and then I will tell you how to do the, then we will do the construction. If I do this, then it means that with respect to A1, B1 to B2 dash, that motion should have happened along a circular arc. Okay. In this case. So, that is how I know that A1 should be the center of that circular arc. So, this is what I will use in my construction. Okay.